Hello everyone and welcome to this new tutorial series in which we are going to go in depth on the material modeling of ductile metals in ABAQUS. There are so many things to discuss under this topic. We are going to start today in this our first tutorial with the basics and basic definition when you are defining a ductile metal in ABAQUS, and we are going to use steel as the most popular material used in ABAQUS by structural engineers or mechanical engineers in general. And we are going to focus today on the basic definition of the elastic range and the plastic behavior of steel or metals in general. So I will start by showing in these slides the theoretical basis for the definitions and the entire process, and then I'm going to show you using an Excel sheet the step-by-step procedure to convert an engineering stress strain into a true stress strain and organizing the data for ABAQUS input. So let's start first by the basic definitions of ductile metals in ABAQUS. We have three basic definitions. We have the elastic property, which is the elastic response, again similar to any other material that you define in ABAQUS. And then you have the plastic property, where you are going to define the plastic response of your material under compression or tension. Of course, this doesn't matter here when you are doing in metals. Pretty much the behavior is the same in both under both types of stresses, compression and tension, unlike concrete. And you define as well like the flow rule and the evolution of the yield surface, or what we call the hardening rule. And the third sub-option that you can define for metals is the damage property. What does damage mean here? So damage means the strength softening of the material and the deterioration in stiffness. And you can add additional things to damage like element deletion or complete failure and so on. So today we are going to focus on the first two parts, the basic definition, the elastic and the plastic part. So let's start by what you have. Well, in general, when you are defining some kind of metal like steel or stainless steel or aluminum or something of that sort, what you typically do to characterize the material behavior, the most basic test that you can do is the uniaxial tensile coupon test. And in this test, you have like some kind of coupon with some dimensions. There are different dimensions for these coupons, rectangular ones, cylindrical ones, and so on. This is not a key issue here, but anyway, so you have some kind of coupon that you pull under some kind of displacement and you measure the force. And from this test, it's a uniaxial test, so you're just pulling in one direction until failure. And when you get from this, you get this kind of red curve. So this is the relation between the stress and the strain for the material. So this curve that we see here, it can be divided into three specific regions. The first region here, so this is the elastic part. So you have the linear part of the relation, the modulus of elasticity. So this is the elastic part until you reach the yield stress or the yield strain. And then following this point, you start getting some hardening. So this is the hardening region. And then you can identify this point. At this point, necking happens. So what does necking means? Well, necking means that this area in the middle will start to neck. It will start to get smaller because of stress concentrations at this location. And then you are getting necking, and then you're getting a drop or an apparent drop in stress until, so this is the softening branch. Okay, this is not real, this drop, we'll discuss this in a second. So you're getting this apparent drop in stress capacity until you reach the final point, and this is the final point where the entire coupon fracture in a ductile manner, of course. So the ductility here comes from this entire range of inelasticity after the elastic range. So this is what makes the metal ductile, which is a good property. So this stress strain curve that you get from the test directly, this is what we call the engineering stress strain curve. So why do we call it like that? Well, when you are conducting the test, you are computing, or you're your controller or the computer or whatever is computing some kind of stress and some kind of strain to do this plot. So how are these computed? Well, they are computed simply by measuring the displacement that you are pulling the specimen, and then you divide this by the original length of the coupon. So if your coupon is like 40 centimeter or 30 centimeter, so this value will be constant, and then you increase the strain. And when you are computing the stress or the engineering stress, you divide the force, whatever the machine is recording, this force, by the original cross-sectional area of your coupon, or a node. So what happens here, that you are dividing by a constant, and over here you are dividing by a constant as well. But this is not entirely accurate. When we do this computation, this is what we call the engineering stress strain. That's fine. But in reality, this doesn't represent the true behavior of the material. Because as we know, when we are pulling here on the coupon, what happens is that the length at any given time changes, because the length of the coupon keeps elongating, and the cross-section area of your coupon starts getting narrower, smaller. So in reality, if I look at any given time, the strain shouldn't be computed like this. It should be computed as whatever the delta displacement that you are applying at the top divided by the total length at this point, previous length at this point, which would be L node plus whatever the value that the specimen elongated until this point. And the same thing, if I'm going to compute the true stress at the critical section, which is in the middle here, then I need to divide the force not by the original area, but by the area at the current time, which in this case is going to reduce. So this is the correct way of doing that. So the question here, when we do this kind of test, we have this kind of engineering stress strain. So what we need to do, we need to transform or convert this curve into the true stress strain curve, which is the true behavior of the material. So how can we do that? Well, first thing, we divide our stress strain curve into two zones. The first zone, this is zone A, let's call it zone A. So this is the zone before necking. So before necking occurs until this point, pretty much before this point occurs, I have my section, my entire coupon elongating in a linear manner, and I don't have any localization of strains at any location within the coupon. So the coupon entirely is elongating. So this is zone A. And in zone A, in order to convert the engineering to the true stress strain curve, the only thing that I need to do is to use these two formulas over here. So I take the engineering stress strain, which is the red curve that I have, and I plus 1, and then I take the natural logarithm of this value, and from that I will get the true strain. For the true stress, I take this engineering stress, and then I multiply this by 1 plus the engineering strain. Now, where did these equations came from? Well, if you search on Google, just write engineering to true stress strain conversion, you will find the process where these two transformation equations were derived. It's a very simple and very straightforward derivation that you can actually do yourself, so it's nothing complicated. And then this gets us pretty much to this. I'm not going to go into those right now, but this is what we finally get for this conversion. So what happens with this conversion? Just notice a couple of things here. So when you do this conversion, what will happen is that the strain values, so the engineering strain values, they are going to become less. So the true strain is a little bit less than the engineering. That's why you see here this point at epsilon u, at the ultimate engineering strain, is going to move a little bit inside with respect to the strain. So there is some shift inside. And again, this makes sense because, as we mentioned, if I'm calculating the true strain, I divide the elongation, the delta elongation, by the total length of the specimen at a given time. But the engineering one, you only divide by the original one, and the original length is always smaller than the current length. So that's why your true strain is a little bit smaller than the engineering one. While the stress, if you're looking at the stress, so the stress is opposite. The stress now will increase. The true stress is going to get bigger, and the more you go into the plastic strains, the larger the increase in the stress value. And the reason because of that, again, we mentioned that when you compute the true stress, you need to divide by the shrinked area at this point, and the shrinked area at this point is always smaller than the original area that was used to compute the engineering stress strain. So you see the difference here, almost negligible in the elastic region, and then it starts increasing. So you see the two curves, the true and the engineering one, diverge from each other while you go into larger strains. So now we're done with this zone A. Then we have zone B. So zone B after necking. So at necking and beyond, what happens is we are getting localization of strain at the middle of the coupon. So we are getting localized strain. So these equations that we used over here don't really apply in this region. So how can we compute? How we can compute the true stress strain until this region? What we can do is we can actually extend this as a straight line. So we extend the true stress strain to a straight line to this point. So the last point that we had over here, and this is the rupture point or the total failure point of my test. So if I really know the true values of the stress and strain at this point, then I can just join the 2 points with a straight line. So how can I get the coordinates of this point over here with respect to the true stress and the true strain? Well, for the strain, you can still use the same equation that we used before, the logarithm of 1 plus the engineering value of epsilon at failure. So this is pretty much the same conversion that we used in zone A for the strain. But for the stress, what you can do, you can actually compute this if you know the force. So you already know the force at the end of the coupon test. So you already know the force. But in this time, you just need to divide this by the failure area. So assuming that you actually recorded this failure area, so after you pulled your coupon and your coupon fractured, if you measure the area at the fracture location, then you can use this directly over here, and then you can compute this stress. And then if you do that, then you have this point, and then you just join a straight line. If you didn't do this measurement after the test, which in most cases many do not do this measurement. So if you don't do this measurement, that's fine. You can just extend this line as a tangent here from this point. You just extend it as a straight line. And so this is the alternative way. So you can just extend the stress strain curve in a straight line tangent to the neck point. So it will have a straight line, a linear equation like this one. So you have two constants, A and B, and A will be equal to sigma ultimate true. So basically the ultimate stress value at this point. And B will equal to theta ultimate true multiplied by 1 minus epsilon ultimate true, which is the x coordinate of this point. So you can do that as well, that's fine. If you look in literature, there are other options like some other references you can find in literature that you can capture this not by a linear curve but with some kind of a power relation, nonlinear relation, and then you have some kind of constant and you can compute the constant like this. Again, the literature have other ways of defining this part. But in most cases, it doesn't really matter a lot. So you can just do the straight line approximation. It should be fine for most applications. So that's it. So what we have right now, we have the entire true stress, true strain behavior of the material. And as you observe right now, this is actually the true behavior of metals and steel in that example that I'm showing here, is that the material, the stress always increases. So it doesn't drop, the material doesn't soften. So unlike concrete, if you refer back to the video that we did on the concrete material, the curve doesn't soften. So the stress keeps going up. All right, so this is a very important thing to note. So now if we go to ABAQUS, so when you are defining an ABAQUS, okay, you can define the density. That's fine if you're doing something with explicit analysis. And then the first thing that you need to define is to define the elastic behavior. And the elastic behavior, well, if you have now the converted true stress strain, then you just need to compute this slope. So if you identify this point, sigma y, you divide it by epsilon y, then you can get the modulus of elasticity. And then under the elastic property, you just need to specify the elastic modulus over here and the Poisson ratio. So that's it for the elastic part. For the plastic part, you need to transform your entire stress strain curve into the plastic part only. So you need to compute the plastic strain, epsilon plastic, and this will be equal to the true one. So the total strain minus epsilon y. Epsilon y is the yield strain, which is basically the yield stress divided by the modulus of elasticity that we previously computed. And when you do that, then the original curve, the total strain curve, is shifted like this. So now you have sigma y at a plastic strain of 0, and then when you go with plastic strains, then your curve goes like that. And then pretty much this branch over here, which is the plastic strain, because again, when you define here in ABAQUS, when you define the plastic, you define with respect to the plastic strain, not the total strain. So then you need to provide the two fields, the data for this entire one, which is the yield stress and the plastic strain. And notice here that the first point is the yield stress and the plastic strain corresponding to it is 0, which is this point over here. Now, if you don't have this coupon data, there are other ways of defining these curves. So if you have just the yield stress and you have, let's say, the failure stress or this ultimate stress, there are different, again, nonlinear functions that you can find in literature to generate this nonlinear curve, this hardening curve, pretty much this plastic region for different types of materials using some kind of nonlinear equation. Of course, in this nonlinear equation, you will have some kind of constants, and this constant that can be obtained by calibration. Or if you look in the literature, you can find values for this or recommended values for these constants for specific types of, let's say, grades of steel or grades of stainless steel or any other material. If you don't want to go into the nonlinear, you can just simplify that, and then you can just assume that the plastic part has a linear function. So in that case, you just need to define 2 points, the yield point, which is at plastic strain 0, and another point at, well, at any location, pretty much at any location of strain. So if you define this, what you have is bilinear material behavior. So you have the elastic branch and then you have some hardening branch. Just be careful here about this point, the last point that you define. Be aware here that ABAQUS will not, so if you're providing this is the last point, ABAQUS is not going to extrapolate if the strains exceeds this value. ABAQUS is not going to extrapolate beyond this point. Instead, what actually ABAQUS is going to do is going to assume that the stress is constant beyond this point. So just be aware of this fact. Of course, the simplest way of defining the plastic region is just to define just a single point, which is this point. And in that case, you have a constant stress. So that's it. Basically, you have an elastic, perfectly plastic material. So you have the elastic range. And then once you reach the yield stress, that's it. You don't exceed the yield stress and you remain constant. Now, of course, here you will notice that you have some other options when you are defining the plastic region, which is the hardening rule. And there are a number of options that you use here to define the hardening rule. This we are going to explain in more detail in another tutorial because it needs further details and it's a more broader subject. But you just need to know at this point that the hardening rule, the type of the hardening rule, it doesn't really matter if you are doing a simulation involving monotonic loading. So if you are doing a simulation like pulling something, or maybe doing a coupon simulation or something just in tension monotonically, it doesn't matter which hardening rule that you are using. These things start to kick in once you start doing cyclic loading, which we are going to discuss in another tutorial. So this is the basic description of defining a metal plasticity or ductile metal plasticity in ABAQUS. Next, we are going to go to an Excel sheet and show how to do this in specific details in Excel, just to follow up on what we discussed here in terms of equations and so on. So right here I have an Excel sheet and in this Excel sheet I have here the engineering stress strain data, so epsilon and sigma. The data are organized over here. So this is the first thing. I have here the units in sigma are in megapascal, and the strain of course is unitless. The first thing that I did is that I identified from the data, I already plotted the data over here on the right. So this is the curve, how it looks like. So we see here that it goes down because this is the engineering stress strain curve. So I identified on the curve the location of the key points. So the first point is the yield point. So this is the point over here at 367 megapascal. So this is the yield point, the end of the elastic branch. In the same time, I have the hardening zone and I identified this point. So this is the necking point as we discussed from the slides. So this is pretty much the ultimate stress based on the engineering stress strain curve. So this is the point over here. And then the third zone, so this is the softening zone. At the end, this is the last point. So this is where rupture or total fracture or failure happened. So this is the fracture point or rupture point, however you want to call it. So this is the last point. So I identified here the three branches just to organize the data. Again, I'm using Excel over here, but what the process that you're going to follow, you can do this in Excel, you can do it in MATLAB, in Python, whatever computational platform that you use to process data. Over here, I have the values for area nodes. So this is the cross-section area of my coupon, 880 millimeter square. And I have here the area of the coupon after it fractured. So at the end, I did the measurement and this was the value of the cross-section area of the coupon in the middle at fracture, 539 millimeter square. Again, if you don't have these two values, this is not important. As we mentioned in the slides, there are two ways of computing. This is pretty much for computing the true stress strain curve after the necking point, but it's fine if you don't have those. So the first step that we want to do after we identify these different zones, we want to transform the engineering stress strain curve into the true one. So here I have the second two columns. So this is what I call true stress strain curve. And this is pretty straightforward. So for the strain, as we mentioned, for the strain, we just need to take the natural logarithm of 1 plus the engineering strain, and that's it. And this will apply for all the points, for all the zones. So up till the softening zone, all the zones, the same transformation from engineering strain to true strain is the same. So the logarithm of 1 plus the engineering strain. Now for the stress, the equation that we are going to use for the transformation, we are going to take the engineering stress and then we multiply it by 1 plus the engineering strain. And this equation, it doesn't apply everywhere. We are going to apply this equation for the elastic zone. So you can use this equation pretty much for the elastic zone and up till the hardening zone. So this equation does not work in the softening zone. So after necking, as we mentioned, because we are getting stress localization and the area is not changing in a linear manner. So it doesn't apply over here. So we stop with the transformation at this point. Now, if I go ahead and superimpose the plot for the true stress strain curve, so this is what I get. As you see, they are pretty much almost the same, very, very small changes when it comes to the elastic range. And then we have here in blue the true stress strain curve up till the necking point. So this is the transformation, but we're still missing this part after the transformation, after the necking point. So before I go and do the transformation for this part following the necking point, let's go ahead and transform this curve, which is with respect to the total strain, to the only plastic part. So this is what I have here. So again, we're still looking at the true stress strain, but we want to compute here the plastic strain. So when we are going to do that, of course, the elastic branch or the elastic zone will be removed. And then you are going to start here from the elastic point, and the computation that you need to do for computing the plastic strain, you are going to take the total strain that you computed over here and subtract from it the strain at yield or epsilon y. So this is the one over here. And this will apply again for all the data up till again the necking point. For the stress, nothing changes here for the stress. We're just transforming, we're just removing the elastic component for the strain. So the stress remains the same as the one that we just computed. Now the thing here that I can do, since this is the plastic one, that we stopped here at the necking point, since we want to compute the extension of the true stress strain curve into the softening zone, so we need another data point, the one in red here. And this data point that I'm showing over here, it's pretty much the one at the end, which is computed based on the equation that we mentioned. So I just took the value of the engineering stress at the last point, and I multiplied this by the area at the original area node, divided by area failure. And this gives me the true stress at the last point or at the rupture point. And then I just moved it over here so that when I can plot this curve, so let's see the curve over here. So this is the curve over here, the plastic strain with respect to the stress. And we can see here the entire curve like that. So you can see that this part following in the softening zone, following the necking point, is a straight line. Again, if you don't have these two pieces of information, that's fine. You can just go here to this point and just extrapolate this curve with a straight line. So if we just plot here up till the necking point, so what you can do in this case, you can do this by the equation that we showed in the slides, or you can do this manually like this. For instance, extending a line, and then you can see that this point at the end is like 0.2 and 650. So you can just put the point here like 0.2, 650. So you can do this visually, or you can use the equations that we showed in the slides, or any other equations in literature that might include some nonlinear approximation. So that's it. This is the process for transforming the engineering stress strain into the true one. It's a straightforward process. The next thing that you need now, you have right here, this is the plastic strain and the stress data that you need, these two sets of data that you need to copy and paste in ABAQUS to define the plastic part. For the elastic slope, you can come here and then you can compute the modulus of elasticity, and then you can compute this based on the true stress strain. So you just take the value of the true stress at yield and divide it by the true strain at yield, and then you get the value of the modulus of elasticity. And again, just for reference, I put here the values of epsilon y, sigma y, epsilon ultimate, and sigma ultimate based on the true. Again, these are all based on the true stress strain. So this concludes our tutorial. I hope you found this useful, and I'll see you in the next one.